Logarithms always seem to give students trouble, and I want to just make you aware of some things. And maybe what I'm about to say is the reason that you feel some discomfort when dealing with logs. So, the way you've introduced to logs right now is the following. We have some expression like this, and we're asked what is log base 2 of 4. And then we are let know that one way of viewing this is that this is the base of this is my exponent which equals 4, and indeed I see now, yes, the x must be a2, right? So if I solve this, it's just a matter of recognizing that the 4 can be written as 2 squared, and then the x again must be a 2. Great. But we keep doing this, and you start to wonder, wait a minute, how come we're not doing I don't know, some other type of calculation? We seem to be converting it to uh, exponential form to get anything out of this. All right, let me first point something out to you. There's something hidden also with dealing with exponentials, but in the examples we do, we never really expose you to this, and the few times when you're exposed to this, it's sort of masked a lot. So you, for example, if I said what's 1.7 to the third power, I'm sure you would grab your calculator immediately and figure this out. Now this we can figure out by hand, but we'll grab our calculator, not an issue. Um, if, for example, I want to do the square root of 4, all of a sudden I know this answer to this because I know what the meaning of this is. But if I want to do square root of 3, I would again grab my calculator and somehow, however the calculator is doing it, is masked. For some reason, this doesn't bother people as much, but because we're going to do things with a log, this seems to bother people a lot more. So some things to point out to you is that the log, as you're seeing, is the inverse function of the exponent. And so this is really a function. And if I were to write this properly, it should be written like this. Log base 2 of 4 is 2. But you'll notice often we omit the parentheses. This is really function notation. That's what this log is. But because it's very specific, don't use the letter F. We give it its new symbolism, but it really is log. And then we sort of mask how it's doing this. So at some point you might start wondering, how is this even possible? I mean, do I have to do this all the time? Well, let me stop here for a sec. The log is a very special type of function called transcendental function. And what is a transcendental function? Oh my gosh. Uh, it is an analytic function that does not satisfy a polynomial equation, in contrast to algebraic function. In other words, here's the issue. A transcendental function transcends algebra and cannot be expressed in terms of a finite sequence of algebraic operations. So here's the key. I can't express it using just my normal order of operations, add, subtract, multiply, divide, in a finite sequence, meaning I get to begin and stop just using these operations. And you'll notice the exponential is the transcendental function. So it's the log and these other things called trig functions. So what do we mean by that? It just means a polynomial, like a line. We'll talk about polynomials later. I can just use multiplication and addition or subtraction, my basic operations, to come up with a value. I enter 2 here, and I could just do these order of operations in a finite process and come up with my value. Here, I cannot do this all the time. So if I wanted to express this, this is not a problem. But I would have issues if I entered the wrong numbers, and this is no different than exponents. If I just enter the wrong thing, let's say now I am at a bind to try and figure out what this is using a finite set of operations. So here's what's happening. So I'm just going to let you see under the hood for a moment, and we can shut it, and then now you start realizing there's something behind the scenes, and we're not going to go there. Okay? So here I am in Desmos, and if I type log, and this is log base 10 of x, I get my graph. And there's my graph right here. If I come over here, I go log, and I entered 3, and somehow magic, it gives me the log of log base 10 of 3 is this value. And of course, if I take 10 and raise it to, again, notice I can't quite do it. No matter how hard I try, I'm not going to be able to get there. So you see there's a problem here. I'm going through a process that it's not finite. It's infinite. And no matter how hard I try, look, I'm trying to pick as many numbers. Notice I can't get to that 3 again. So this number is not correct. This is what the computer's spitting out. And that's as close, notice, I can get to 3. So log of base 3, this is as close as we can get. When I try to reverse a process, I can't quite get there because this is not the exact set value. This has been rounded. All right, the question becomes, what exactly is going on here? The log is well defined, but the definition doesn't mean we can express it in a finite set of operations. All right, hang on for 1 second. And if I even type the natural log, let me do the natural log as well, of x. Here's the natural log of x. And again, I let the computer, and it can find me values. But if I try to reverse, just like the other one, I'm going to be not going to be able to get that 4 back again, not using this sequence of numbers. All right, so what is a computer doing? I'm going to shut this one and just concentrate on the natural log. All right, the computer's doing the following. I'm going to see if I can bring this up here. Okay, so there is some form of formula in your computer. It might be this. I would imagine nowadays it's a lot more sophisticated than this. But this is what's being typed into your computer or programmed. The problem with this is that it starts with one term and it does equal as long as you can go to infinity, which of course we can't. So there's a little fix for that, but that's why a calculator can only give you so many decimals numbers of accuracy. The process itself is infinite. It cannot give you an exact number, but it can give you to whatever decimal place you desire. So I'm going to type the following, just to again be clear that nothing here is untoward. I'm going to call this now function g of x, so you can see it. Again, nothing's happening. It's still the same function, g of x, and just to prove the point, you saw this value. If I just type g of 4, I just renamed it. It's the same number because I just redefined this natural log of x as g of x. Again, you'll see in a second why I'm doing this. So now I'm going to create, as best as I can, this formula, and I'm going to stop the video and keep pushing it forward to speed this up. It's going to take me a while to type these things. So now all I've done is typed in the first 3 terms of this sequence. I start up with n equals 1. When I put it here, I get the -1 raised to the second power. That's +1. So now I go on, I make this a 1, I make this a 1, and it gives me this first term, x minus 1. And then I keep changing. The next one is n equals 2, n equals 2, and -1 cubed is -1, and then I put a 2 here and 2 here, and that's what you see here, and I continue in this manner. What is the result of doing that? Notice the green line is what I just finished typing. The black line is what the computer says is the natural log. Okay, so I'm going to continue typing in here. Okay, so I've continued typing more terms. Now it's going off screen. If I move this a little bit, notice all that I've typed into it so far, and notice now, look at the green line now. It's mimicking a lot better. You'll notice it seems to be matched right here in this little domain. It seems to match perfectly. Let's just try this out. If I type g of, let's see, this is 1, so let me make a little 1.2. So g of 1.2 is this. This is what the computer's doing, which has a very good approximation. And now this is my weak attempt using my little formula here. And what does it come out? Hey, look at that. Here's the computer saying, here's what I'm saying. Okay, I'm going to go continue typing some more in here. Hang on. Okay, now I finished typing some more. Notice I'm up to 11 terms. And the green line you see right here is the one I keep typing in. The black line is, of course, what the computer is doing. And it's, again, has a different algorithm. But what I'm trying to show you is that the natural log, to express it, I will need an infinite amount of terms to do so. But I can do it. Well, sorry, I can't do it. I can't write an infinite number of terms, but I can get it down to a certain level of accuracy, decimal accuracy. Notice by just typing in those more terms, here is mine, this bottom one, h of 1.2, and here's the computer's version, which is correct to that last decimal. And you'll notice now that I've gotten very close. Look at that. Let's see, what's the last digit? This 5 is the last correct digit. And then if that, we differ. So if I kept typing some more, I would get a better and better approximation. So there's something like this typed into your computer or your calculator. The version in your calculator is way more sophisticated. And what do we mean by sophisticated? What I mean is there's something just like this typed into it, but it doesn't have to be as many. Sophisticated just means that I can get a very good approximation without having to write as many of these terms out. But that's all that's happening. So that what I'm writing is just using addition, multiplication, division, everything you've encountered before. That's all I'm doing. And if I look closely, what this is, we'll eventually call, the polynomial, which is in the same, it's a general family that a quadratic and a linear equation belong to, and we'll see that later in the course. But there you have it. This is what's really behind the scenes, and this is why we need a calculator to find the natural log of something like 4. I'm blowing these up so you can see the two graphs, and you can see that now we can't tell the green line from the black line, and that's why notice these numbers are extremely accurate, probably more accuracy than we care to have.